So I think I'm gonna start from where I stopped before. Let me open up the stream on the other monitor. So I found this stuff here that I was reading after I closed the stream about theme parts. There's also these videos here to watch. Yep, this. Oops.
We will also see how it behaves both in module level and package level. Let's get in. Before that, we need to understand a concept called wildcard import. Some people also call it as star or asterisk import. Let's look at an example here. Here I have a sample model. In this model, there is a private function which starts with an underscore, and we have helper function, and we have not implemented function, which will raise not implemented error exception if user calls it, and we have public function. Now coming back to main.py file where I am importing using wildcard import, I can see what are the objects that I have available in the scope using dir function. The dir function without an argument will print all the objects that I have available in the current scope. In this example, it is a module scope. Let's try to run this program and see what I will get in the output. You can see I have access to the helper function and the not implemented function and the print function and the public function. The print function I have imported it as well. What the wildcard import do in Python is it will load or import all the objects excluding the ones that are starting with an underscore. That's why we are not seeing here the private function. To override this default behavior of wildcard import, you can use Dunder all variable. Let's enable this code snippet and try to run our program again. Now you can see I have only access to the public function in the main function scope, but you can still import the not implemented function using named import. The Dunder variable only applicable when you are using the wildcard import, which is not a good practice to use in Python, but you can still use it if you prefer to use. But one thing you have to remember here is using this one. If you use wildcard import inside the function body or a class, it will raise an exception here. In this case, it says that wildcard import not allowed within a class or function. So it is not applicable. Let's look at another example why wildcard import is a bad example in Python. Let's enable these two lines and call read CSV function and zeros function, which works perfectly fine. The problem with this code snippet is if there is a junior developer who joined our team after a couple of months, he has no idea where the read CSV function is coming from and zeros function is coming from. Pause and the package under all. Package. Let's first understand the structure of the package before we can understand the Dunder all variable. Let's first understand the directory structure of the package before we can go to the Dunder all. Here I have a package with the name of package, and we have inside that we have subpackage 1 and the subpackage 2. Inside subpackage 1 we have a module, and inside subpackage 2 we have module 2. Let's look at what those are. In the module 1 I have a module 1 function which will just print module 1 function, and I also have the Dunder all like the way we look at earlier in the module. In the similar way I have module 2 function, module 2. In the module 2 I have module 2 function. In the similar way I'm having Dunder all. And going back to the subpackage level in80 file, I have imported it from the module 1 from here to here, the in80 file, and I'm propagating it to the above level using the module 1 dot and Dunder all. Okay, it's just way
I don't
propagating it to the
understand
top.
really well what it's saying. I guess it's just imports all.
Another topic we want to look at is the optional Dunder all attribute of modules. Dunder all lets you control which attributes are imported when someone uses the from module import star syntax. If Dunder all is not specified, then from x import star imports all public names from the imported module. Dunder all must be a list of strings, and each string indicates a name which will be imported when the star syntax is used. For example, let's see what import star does if we import our compressed modules. What we see is that import star imported the bzipped and gzipped submodules of the compressed package directly into our local namespace. What we might prefer is that import star imports the different opener functions from each of these modules. Let's update compressed dunder-init.py to do that. Now, if we use import star on reader.compressed, we get the two opener functions with new names. So Dunder all can be a useful tool for limiting what names are exposed from your modules. We still don't recommend that you use the import star syntax as a rule, but it's good to know about Dunder all since you're likely to see it in the wild.
Nice. Okay, I think I understand now. So I was looking at this thing here. Yeah, so first it searches for the module, then it loads it, and then it bounds it to a namespace. Of course, in normal code, you should prefer the former. One thing to note is that even when you import only one attribute from a module, the whole module is loaded and executed. The rest of the contents of the module just aren't bound to the current namespace. One way to prove this is to have a look at what's known as the module cache. This is modules math.cospi. These modules acts as a module cache. It contains references to all modules that have been imported. The module cache plays a very important role in the Python part system. The first place Python looks for modules when doing an import is in sys.modules. If a module is already available, then it isn't loaded again. This is a great optimization, but is also a necessity. If modules were reloaded each time they were imported, then you could end up with inconsistencies in certain situations, such as when the underlying source code changes while a script is running. Recall the import path you saw earlier. It essentially tells Python where to search for modules. However, if Python finds a module in the module cache, then it won't bother searching the import path for the module. In object-oriented programming, a singleton is a class with at most one instance. While it's possible to implement singletons in Python, most good users of singleton can be handled by modules instead. You can trust the module cache to instantiate a class only once. As an example, let's return to the United States population data you saw earlier. The following module defines a class wrapping the population data. Reading the data from the disk takes some time. Since you don't expect the data file to change, you instantiate the class when you load the module. The name of the class starts with an underscore to indicate to users that they shouldn't use it. You can use the population.data singleton to create matplotlib graph showing the population projection. Note that the loading data imports, blah blah. Reloading modules. The module cache can be a little frustrating when you're working the interactive interpreter. It's not trivial to reload module after you change it. As part of testing and debugging this module, import in a Python console. Let's say you realize that you have a bug in your code, so you update the number by file in your editor. Return to your console, you import the updated module to see the effect of your fix. Why is the answer still 24? The module cache is doing its now frustrating magic. Since Python imported a number earlier, it sees no reason to load the module again even though you just changed it. The most straightforward solution to this is to exit the Python console and restart it. It forces Python to clear its module cache as well. However, restarting the disturbance is now as feasible. So this is just stuff that is not that useful for me, I guess. Finders and loaders. We saw earlier that creating modules with the same name as standard libraries can create problems. For example, if you have a file named math.py in Python's import path, then you won't be able to import math from the standard library. This isn't always the case though. Create a file named time.py with the following content. Next, open up Python interpreter. Something weird happened. And instead, it imported the time module from the standard library. Why are the standard library modules behaving consistently? You can get a hint by inspecting the modules. You can see that math is imported from a file, whereas times is some kind of built-in module. It seems that built-in modules aren't shadowed by local ones. Note the built-in modules are compiled into the Python interpreter. Typically, they are foundational modules like built-in, sys, and time. Which modules are built-in depends on your Python interpreter, but you can find their names in sys.built-in module names. So let me try to do this in the PyCharm and see what happens. I have to import sys here, I guess. Also, it does print something. I'm gonna use pretty prints as well, so it's easier to read. It's a list of all the imported, all the built-in modules. Math, Marshall, Intercourse, GC, CMath, built-ins, Binance C, the converter thing, array, subinterpreters, warnings, threads, struct, string, statistics, some crypto thing, SHA-256, I think is the most used one. Random Pico, operator, JSON. Oh, so I remember one time I used this and it gave me a warning and I didn't know why. I understand. It's a private class, so you shouldn't be using it. But on Stack Overflow, people recommend it sometimes to solve some issues with APIs. Daytime CSV. This is very useful to know, I guess. Pandas and NumPy don't seem to be built-in modules. Yeah, I don't see them here. So let me go back. Let's dig even deeper into Python's import system. This will also show why built-in modules aren't shadowed by local ones. There are several steps involved when importing a module. Python checks if the module is available in the module cache. If sys.modules contains the name of the module, then the module is already available, and the import process ends. Python starts looking for the modules using several finders. A finder will search for the module using a given strategy. The default finders can import built-in modules, frozen modules, and modules on the import path. Python loads the module using a loader, which loader Python uses is determined by the finder that located the module and is specified, and it is specified in something called a module spec. You can extend Python import system by implementing your own finder and, if necessary, your own loader. Nice. You see a more useful example of a finder later. For now, you'll learn how to do basic and possibly silly customizations of the import system. Sys.metapath controls which finders are called during the import process. Oh, this article is really good. So, let me think now. I think I need to write these things down. Write them before everything here. So this is, oh, I forgot that this thing copies the wrong way. This shows built in modules. Built-in modules are, I guess, the difference is they come from Python, if I remember correctly. Yeah, that's what I'm gonna put there. If it's wrong, then so be it. Depends on the interpreter as well. So I think it depends on the IDE as well. The sys meta path is also a really good thing to know. You can send the Python import system by implementing your own finder and, if necessary, your own loader. You'll see a more useful example of a finder later. For now, learn how to do basic and possibly silly customizations of the import system. This metapath controls which finders are called during the import process. So it's Times New Roman. This fucking thing. There we go. So import sys.metapath. Frozen import lib, built-in importer. Frozen import lib, external path finder. First, note that this answers the question from earlier. Built-in modules aren't shadowed by local modules base because the built-in finder is called before the import path finder. So first it calls this, then it calls external path finder, which finds local modules. Second, note that you can customize this meta path to your liking. I guess I'm gonna take a picture of this as well, just in case. Path finder. If you quickly mess up your Python session, you can remove all finders. No module named math. So file standard in. So this comes from C, I guess. I can already see how learning C++ helps on understanding the other stuff. So I guess it isn't a waste of time. Not imported at startup, still in the module cache. Module import lib from this file. If there are no finders, Python can't find or import new modules. However, Python can still import modules that are already in the module cache since it looks there before calling any finders. The example above, import lib, was already loaded under the hood before you cleared the list of finders. If you really want to make your Python session completely unusable, then you can also clear the module cache. sys.modules. Sys.modules is the module cache. I'm not sure if I'm saying that the right way as well. I didn't put it in here, but whatever. Let me see on Google translations.
Cache.
Cache. Yeah, cache.
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 It's the same pronunciation. The following is a slightly more useful example. You write a finder that prints a message to the console identify the module being imported. The example shows how to add your own finder, although it doesn't actually attempt to find a module. Debug importer.py. Import sys class debug finder class method def. So this is a wrapper, I guess, a decorator function. I'm not sure, but I believe that's the case. Def find spec cls name path target equals none. F importing name this return none. sys.meta underscore path that insert 0 debug finder. All finders must implement a find spec class method, which should try to find a given module. There are two ways that find spec can terminate: by returning none if it doesn't know how to find and load the module, by returning a module spec specifying how to load the module, by raising a module not found error to indicate that the module can't be imported. The debug finder prints a message to the console, then explicitly returns none to indicate that other finders should figure out how to actually import the module. Note, since Python implicitly returns none from any function or method without an explicit return, you can leave out line 9. However, in this case, it's good to include return none to make it clear that debug finder doesn't find a module. I don't understand this function really well, so I'm gonna put it here and then I'm gonna search later after I'm done with this article. Don't understand what the decorator function does there. Sys.meta path. Oh, it's the same thing that I have written here that I already forgot, which controls which finders are called during the import process. So it inserts this function here, and the 0, I'm not sure why it's there. Inserts this class, I should say. Def find spec, cell name, path, target none. All finders must implement. Yeah, already read that. The debug finder prints a message to the console and then explicitly returns none to indicate the others finders shouldn't blah blah blah. Note, since Python implicitly returns none from any function or method without an explicit return, you can leave. You already read that. By inserting debug finder first in the list of finders, you get the running list of all modules being imported. Also, it prints out which modules are being imported. I guess. I print importing name. Because it's gonna run this file anyway because it doesn't have the name specified. So when it imports the file, it runs this code. And this has this sys meta path, which inserts this function, this class into the finder, which makes it this line run, which is gonna print the name of the thing that is being imported. You can, for instance, see that importing CSV triggers the import of several other modules the CSV depends on. Note that the verbals option to the Python interpreter, Python /v, gives the same information much more. For another example, say that you're on a quest to read the world of regular expressions. Now, why would you want such a thing? Regular expressions are great. You could implement the following finder that bans the regular expressions module. So it's the same thing, but if name is banned modules, raise module not found there. Yeah, but I don't understand. Yeah, so here I guess naming banned modules. Oh, it's here. So it's declaring here which ones is gonna ban. Raising a module not found error ensures that no finder later in the list of finders will be executed. This effectively stops you from using regular expressions in Python. So one thing I can do already that I'm thinking, I can do this function here that I did on the beginning, and then I can use the print statements or the name of the function in order to find the other ones. Because every import is going to have a list of imports that is dependent on. And that way I probably can build the thing maybe. But I'm not really sure. It seems like it's possible. And I guess the imports are the connections because, yeah. I imagine it's going to be a very large tree if it works. Because everything is going to be interconnected with a bunch of other modules. Even though you're importing only CSV, that module is importing re behind the scenes, so an error is raised. Example, automatically install from pipe. Because the Python import system is already quite powerful and useful, there are many more ways to mess it up than there are to extend it in a useful way. However, the following example can be useful in certain situations. Python package index pipe is a one-stop cheese shop for finding third third-party modules and packages. It's also the place from which pip downloads packages. Python package index. And the list of tabs keeps growing. It's insane. In other real Python tutorials, you may have seen instructions to use Python/m pip install to install the third-party modules and packages you need for following along with examples. Wouldn't it be great to have Python automatically install missing modules for you? Warning, in most cases, it really wouldn't be great to have Python install modules automatically. For instance, in most production settings, you want to stay in control of your environment. Furthermore, the documentation cautions against using pip this way. To avoid messing up your Python installation, you should play with this code only in environments that you wouldn't mind deleting or reinstalling. The following Finder attempts to install modules using pip. So from imports, lib import util, imports the process sys, then creates this class again, uses define spec, and now prints module name not install attempting to pip install. cmd dot equals. So I'm trying to think, how can I run this function recursively? Try subprocess.run command split check equals true, except subprocess calls process error, return util finds back sys.metapath.append. Pip finder. Compared to the finders you saw earlier, this one is slightly more complicated. By putting this finder less in the list of finders, you know that if you call pip finder, then the module won't be found on your system. The job of .findSpec is therefore just to do the pip install. If the installation works, then the module spec will be created and returned. First, use the parse library without installing it yourself. Module parse not install, attempting to pip install, collecting parse, downloading parse. I guess these examples they show is on the terminal. Normally import parse would have raised a module not found error, but in this case parse is installed and imported. While the pip finder seemingly works, there are some challenges with this approach. One major problem is that the import name of a module doesn't always correspond to its name on pipe. For example, the real Python feed reader is called real Python reader on pipe, but the import name is simply reader. So I guess I'm gonna come back to the first one they did, which is this one. So I'm gonna erase this stuff here, and then I'm gonna see what happens when I run this from another file. Sklearn. Nice. That's crazy. So it really shows. Damn, that's a bunch of files. It's insane. So it uses SciPy. Oh, that's so nice. I thought it would be a lot harder to find what I wanted, but it seems like I'm gonna probably be able to do it with this. Importing SciPy stats. Optimize SK sparse. Unit test, arg parse get. Unit test this. The issue though is how can I run those files? The imports on those files. sklearn, string threading, quick graph, SHA 512. So sklearn uses NumPy as a built-in module. So now let me see here. Debug Finder. So name is the name, is what I'm printing every time I run this. So how can I import? The problem is if I put import name, I'm not sure if it's gonna do what I wanna do. So I have to think about what this thing is doing so I can call it recursively when I run the file. So it finds all the modules from all these modules until it finds everything until the bottom of the thing, to the bottom of Python, and choose C. So I need to understand what class methods is. I think I'm gonna keep reading the article and then try to figure out what that is, but I think I'm on the right path here. This could have disastrous consequences for our project. I also have to read all this documentation about it, about the imports. I think that might help as well. Yeah, this is the pip stuff. Using pip finder to import install, reader ends up installing the wrong package. Import pip importer, import reader. This could have disastrous consequences for your project. One situation in which automatic installations can be quite helpful is when you're running Python in the cloud with more limited control over your environment, such as when you're running Jupyter-style notebooks and at Google Collaboratory. The Colab notebook environment is great for doing cooperative data exploration. Typical notebook comes with many data science packages installed, including NumPy, Pandas, and Matplotlib. And you can add new packages with pip, but you can also activate automatic installations. So class pip finder, meta path finder, add class methods, then find spec again. And I might also try to find for videos about that. Not installed, attempting to pip install. sys.executable and pip install. Try subprocess.run, command split, check equals true. Subprocess called, process return error. So I don't understand this one. sys.executable and name. So maybe I need to search the sys library first. Again with the other ones. So where is this thing? Python libraries. Yeah, was on the bottom now. Climb to the top. Seems like this is the most important library to understand because it comes before all of the other ones. If I'm understanding this correctly. Since pip importer isn't available locally on the Colab server, the code is copied into the first cell of the notebook. Example, import data files. The final example in this section is inspired by this guy. Great blog, posts import almost anything in Python, and intro to module loaders and finders. Nice, want to read that as well. You've already seen how to use import lib.resources to import data files. Here you will instead implement a custom loader that can import a CSV file directly. Earlier, you worked with a huge CSV file with population data to make the custom loader example more manageable. Consider the following smaller inplace.csv file. The first line is a header naming 3 fields, and the following 2 rows of data each contain information about an employee. For more information about working with CSV files, check out reading. Don't need this. Your goal in this section is to write a finder and a loader that allows you to import the CSV file directly so that you can write code like the following. So to write a finder and a loader that allow you to import the CSV file directly. Per row in place data. The job of the finder will be to search for and recognize CSV files. The loader's job will be to import the CSV data. Often you can implement finders and corresponding loaders in one common class. That's the approach you'll take. So I guess the finder comes here now. So I also noticed that it's using this thing from C++ as well. So I guess when it's doing functions like this, it has this different import here, which is interesting. CSV pathlib resys for import lib.machinery import module spec. Store path to CSV class method again, then find spec. So this is the whole class of the thing. Store path to CSV file. Package look for CSV file. Package underscore module name equals name.r partition dot CSV file name equals f module name. Directories equals sys.path if path is known as path. For directory, in directory CSV pathlib.path directory underscore CSV file name. If CSV path.exists, return module spec. Def create module, returning none, uses the standard machinery in creating modules. Def execute module, self module. Executing the module means reading the CSV file. The self.csv path open as feed rows. Data, field names, create a dict with each field. Values equals zip times row, values for row in data. Fields equals dict, zip fields name values. Add the data to the module. Module.dict, Dunder dict. Dunder dict. Dot update fields. Dict data equals data, field names, module file. Then here the string, the name of the class. Representation of the class. Return f self.class.name. Identifier, create a valid identifier from string. Return this thing here. Add the CSV imported at the end of the list of finders. sys.metapath.append CSV importer. So I guess this sys.metapath is the whole thing, is the file where there is the instructions to find, load, and then attach to the namespace. And this is what these files are doing. When I write code like this, it inserts this class onto the file metapath from sys. Maybe I can use inspect to find out. I think it's probably gonna be on the site packages maybe, but I'm not sure. Get source sys dot. Let me put sys first. Module sys is a built-in module. So I can't get the source. No, I was doing something just like that to find the source of built-in. Let me try .meta. Yeah, so this doesn't work. I think it's this thing. This dot built-in module names shows built-in module name modules. Modules that come with Python depends on interpreter as well. But how do I find these modules? Is the question. It's gonna give me an error. So erase this. And do this instead. Module C is built in. Path. You can make path or a meta path. This one looks interesting as well. Frozen import lib, built-in importer class. Frozen importer. Yeah, it doesn't give me the path of the thing. Maybe this path is gonna work. Yeah, now it works. I guess. Lib inspect. Module finder. Which is the file that I'm on. Anaconda Python zip. Anaconda lib. It's on Anaconda side packages or Anaconda lib. Which lib? This one. Also, there's nothing here. Maybe something happened. I did something here that I don't understand. It still doesn't work. That's weird. I don't know, but at least now I know where it is. So let me keep reading this stuff. I think I'm gonna close the window there because of the noise. There's quite a bit of code in this example. Luckily, most of the work is done in find underscore spec and execute module. Let's look at it in more detail. As I saw earlier, find spec is responsible for finding the module. In this case, you're looking for CSV files. So create a file name with a .csv suffix. Name contains the full name of the module that is imported. For example, if you use from data import in place, then the name will be data.inplace. In this case, the file name will be inplace.csv. For top level imports, path will be none. In that case, you look for the CSV file in the full import path, which will include the current working directory. If you're importing a CSV file within a package, then path will be set to the path or paths of the package. If you find a matching CSV file, then a module spec is returned. This module spec tells Python to load a module using CSV importer. The CSV data is loaded by execute module. You can use a CSV.dictWriter from the standard library to do the actual parsing of the file. I'm thinking about a bunch of stuff, so it's hard to concentrate on the reading. Like most things in Python, modules are backed by dictionaries. By adding the CSV data to module.dict, you make it available as attributes of the module. For instance, adding field names to the module directory on line 44 allows you to list the field names in the CSV file as follows. In general, CSV field names can contain spaces and other characters that aren't allowed in Python attribute names. By adding the fields as attributes on the module, you sanitize the field names using a regular expression. This is done in identifier starting on line 51. Import tips and tricks. To round out this tutorial, you see a few tips about how to handle certain situations that come up from time to time. You see how to deal with missing packages, cyclic imports, and even packages stored inside zip files. Handle packages across Python versions. Sometimes you need to deal with packages that have different names depending on the Python version. If you've already seen one example of this, import lib.resources has only been available since Python 3.7. In earlier versions of Python, you need to install and use import lib_resources instead. As long as the different versions of the package are compatible, you can handle this by renaming the package with S. Try from import lib, import resources, accept import error, import lib resources as resources. The rest of the code you can refer to resources and not worry about whether you're using import lib.resources or import lib_resources. Normally, it's easiest to use a try except statement to figure out which version to use. Another option is to inspect the version of the Python interpreter. However, this may add some maintenance costs if you need to update the version numbers. You could rewrite the previous example as follows. So this checks for the version and then does the same thing. This would use import lib resources on Python 3.7 while falling back to import lib resources or on older versions of Python. So I was having trouble with this with NumPy and sklearn as well, because they required different versions of Python. So this is good to know. This is that version info. See the Flake 2020 project for good and future-proof. Advice on how to check if Python version is running. Handle missing packages using an alternative. The following use case is closely related to the previous example. Assume there is a compatible implementation of a package, then your implementation is better optimized, so you want to use it if it's available. However, the original package is more easily available and also delivers acceptable performance. One such example is Quicktions, which is an optimized version of fractions from the standard library. You can handle these preferences the same way you handle different package names earlier. This will use this name, the available fraction not lost. By renaming your JSON to JSON, you don't have to worry about it. So same thing. Handle missing packages, use a mock instead. Third related example is adding a package that provides nice to have feature that's not strictly necessary for your app. Again, this can be solved by adding try except to your imports. The extra challenge is how you replace the optional package if it's not available. For a concrete example, say that you're using this thing. Unfortunately, the color doesn't render in the example above. So yeah, this is not that important to me. possible to change the return value of string on mock objects, however, in this case, it's more convenient to return on mock. If you run the script on a system in which Colorama isn't available, then it will still work, but it may not look as nice. You should see the same results as earlier. Import scripts as modules. One difference between scripts and library modules is that scripts typically do something, whereas libraries provide functionality. Both scripts and libraries live inside regular Python files, and as far as Python is concerned, there is no difference between them. Instead, the difference is in how the file is meant to be used. Should it be executed with python file.py or imported with import file inside another script? Sometimes you have a module that works as both a script and a library. You could try to refactor your module into two different files. One example of this is in the standard library is the JSON package. You usually use it as a library, but it also comes bundled with a script that can prettify JSON files. Some have the following colors.json file. As JSON is often read only by machines, many JSON files are formatted in a readable fashion. In fact, it's quite common for JSON files to consist of one very long line of text. JSON.to is a script that uses the JSON library to format JSON in a readable fashion. Now the structure of the JSON file becomes much less complicated to grasp. It's a good practice to split scripts and libraries. Python has an idiom that makes it possible to treat a module as both a script and a library at the same time. As noted earlier, the value of special name, module variables is set at runtime based on whether the module is imported or run as a script. Create the following file. If you run this file, then you'll see that name is set to the special value of main. However, if you import the module, then name is set to the name of the module. This behavior is leveraged in the following pattern. Let's use this in a bigger example. In an attempt to keep you young, the following script will replace any old age 25 or above with 24. A def make young replaced by age for W text split. I'm not sure. Oh, here, if name equals main, text input does something. Make young text. You can run this as a script, and it will interactively make the age you type younger. So if you run as a script, it's doing this, I guess. You can also use the module as an importable library. The if test on line 12 makes sure that there are no side effects when you import the library. Only the functions make young and replace by age are defined. You can, for instance, use this library as follows. So it's the same thing that the Corey guy was talking about. For the protection of the if test, the import would have triggered the interactive input and made feel young very hard to use as a library. The import would have triggered the interactive input. Yeah, I got it now. Run Python scripts from zip files. A slightly obscure feature of Python is that it can run scripts packages into zip files. The main advantage of this is that you can distribute a full package on a single file as a single file. Note, however, that this still requires Python to be installed on the system. If you want to distribute your Python application as a standalone executable file, then say using PyInstaller to easily distribute the Python applications. The app consists of the following. Also add the zip. So I guess here is not stuff that I'm interested in anymore. Let's close this section by looking at a nice effort of using import lib.resources, and that should use the following code to open the data file. Resources feed. A more common way to open data files is to locate them based on your module's file attribute. So it uses pathlib.path file parent. It's probably not gonna work. Import lib's not fine. So this approach usually works well, however it falls apart when your application is packed into a zip file. Your data file is inside the zip archive, so open isn't able to open it. Import lib.resources, on the other hand, will extract your data to a temporary file before opening it. Handle cyclical imports. A cyclical import happens when you have two or more modules importing each other. More concretely, imagine that the module in uses import young, and the in and uses import young, and the module young similarly imports in. Python's import system is to some extent designed to handle import cycles. For instance, the following code, while not very useful, runs fine. Trying to import in the interactive interpreter imports young as well. Note that young is imported in the middle of the import of yin, precisely at the import young statement in the source code of yin. The reason this doesn't end up in endless recursion is our old friends, the module cache. When you type import in, a reference to in is added to the module cache even before in is loaded. When Young tries to import in later, it simply uses the reference in the module cache. I also have modules that do something slightly more useful. If you define attributes and functions in your modules, then it always still works. Importing in works the same as before. The issues associated with recursive imports start popping up when you actually use the other module at import time instead of just defining functions that will use the other module later. Add one line to young.py. Now Python gets confused by the import. The error message may seem a bit puzzling at first. Looking back at source code can confirm that number is defined in the in module. The problem is that number isn't defined in in at the time young gets imported. Consequently, in.number is used by the call to combine. To add to the confusion, we have no issues importing young. By the time young calls combine, in is fully imported and in.number is well defined. As a final twist, because of the module cache saw earlier, importing might work if you do some other imports first. So how can you avoid being bogged down and confused by cyclical imports? Having two or more modules importing each other is often a sign that you can improve the design of your modules. Often the easiest time to fix cyclical imports is before you implement them. If you see cycles in your architecture sketches, have a closer look and try to break the cycles. Still, there are times when it's reasonable to introduce an import cycle. As you saw above, this isn't a problem so long as your modules define only attributes, function, classes, and so on. The second tip, which is also good design practice, is to keep your modules free of side effects at import time. If you really need modules with import cycles and side effects, there's still another way out. Do your imports locally inside functions. Note that in the following code, import young is done inside combine. I also saw this stuff, and I didn't know you could do that. This has two consequences. First, young is available only inside the combine function. More importantly, the import doesn't happen to call combine after yin has been fully imported. Now there are no issues importing. Profile imports. I'm concerned when importing several modules and packages that it will add to the startup time of your script. Depending on your application, this may or may not be critical. Since the release of Python 3.7, we've had a quick way of knowing how much time it takes to import packages and modules. Python 3.7 supports the import time command line option, which measures and prints how much time each module takes to import. Yeah, this could be useful, but it's the command line. The cumulative column shows the cumulative time of import on a per package basis. You can read the listing as follows. Python spent 1320 microseconds to fully import datetime, which involved the importing time math and this implementation datetime as well. The self column shows the time it took to import only the given modules, excluding any recursive imports. You can see that time took 87 microseconds to import. The rest, okay. Have a look at the countdown example from the colorless section. This example, blah blah blah. Conclusion in this story, we've gotten to know Python import systems like many things. Yeah, so it doesn't talk about imports from imports. Oh no, the article doesn't exist anymore. An investigation was found in violation of the middle rooms. That's crazy. And so this is the same documentation I have here, I think. It's the same. Yeah, it's the documentation of Python. Built-in module names is a tuple, a bit like a immutable anonymous struct of strings giving the names of all modules that are compiled into this Python interpreter. This.modules, this is a dictionary that maps module names to module objects which have already been loaded. This can be manipulated to force reloading of modules and other tricks. Note that removing a module from this dictionary is not the same as calling reload on the corresponding module object. So modules is a dictionary. To get just the name type, cs.module keys, although it probably isn't that useful. Maybe I should do on the other file. Language print. Yeah, this is the same stuff that I saw before. So let me think. What can I do here? Why would you do that? List of modules that are built in is here. What happens? Their interpreter running Python file. We need to understand. Need to go to that article again, I guess. It feels like such a simple thing to do, but at the same time, it's so hard. Because all that I need to do is use the function to find the names. Then from those names, I need to open up a file. I need to do the same process, but without opening a file. Maybe if I search for how to find all imports a library uses. Right. I'm gonna open this thing again. This one might be good as well. I need to read the documentation before I read this. Module Finder. Find modules used by a script. This module provides a module finder class that can be used to determine the set of modules imported by a script. Module finder py can also be run as a script, giving the file name of a Python script as its arguments. At the reach, a report of the imported modules will be printed. Module finder.add package path. Record that the package name can be found in the specified path. Module finder replace package. Allow specifying that the module named old name is in fact a package named new name. Class Module Finder. Module Finder. This class provides run script and report methods to determine the set of modules imported by a script. Path can be a list of directories to search for modules. I think I'm going to close this inspect file. I don't think the get source function is what I'm looking for. And these other functions here. I think the best direction to go is to study this sys library. So sys metapath. This class runs scripts and reports the list of directories if not specified. Syspath is used. Debug sets the debugging level. Higher level makes the class print debugging messages about what's doing. Exclude is a list of module names to exclude from the analysis. Replace paths is a list of old path, new path, tuples that will be placed in the module paths. Report print report to standard output that lists the module imported by the script and their paths, as well as modules that are missing or seem to be missing. Run script analyze the contents of the path name file, which must contain Python code. Modules, a dictionary mapping module names to modules. Example usage of module finder. The script that is going to get analyzed later on. Bacon.py. So I not only need to find all the modules that a library uses, but how they are connected to each other. That's the difficult part. Because that other function already shows me all the modules, but it doesn't show me the modules that those modules use and the connection between them. The script will output the reports with Bacon. So let me just see what happens if I do something with name here. Maybe if I call find spec name. I want to put the same arguments here. Path target equals no. I'm not sure if this is gonna work, but I guess it's worth trying. Find spec is not defined. Yeah. Oh, I need to use return there. But I'm not sure if this is gonna work anyway. Yeah, it's not defined. I can't call the function because it's gonna give me an infinite loop. I don't think this is the best approach. So think about this. What if I put import name here? It's probably not gonna work. It's already giving me a warning there. Maximum recursion depth exceeded while calling a Python object. And it just gets into a loop. We'll do this. The issue is that I don't understand this find spec really well. This sys thing. Maybe if I do a loop there. Is CLS. Let me get to this point here again. Oh, here. Syspath.insert pathlib.path file parent. This works because the import path includes the folder containing structure.py. The files.py. The issue if this approach is that your import path can get very messy and it's hard to understand. In practice, you're creating a feature of early Python versions called implicit relative imports. These were removed from the language by pip 328 with the following rationale. Python 3.4 and earlier, if you're reading a module located inside a package, it is not clear whether import foo or to a top-level module or to another module inside the package. As Python's library expands, More and more existing package internal modules suddenly shadow standard library modules by accident. It's a particularly difficult problem inside packages because there's no way to specify which module is meant. Another solution is to use a relative import instead. Unfortunately, you can no longer call the app directly. The problem is that relative imports are resolved differently in scripts than are imported modules. Of course, you could go back and restore the absolute import before running the script directly, or you could even do some try except acrobatics to import files absolutely or relatively depending on what works. There's even an officially sanctioned hack to make relative imports work in scripts. Unfortunately, this also forces you to change sys.path in most cases. There must be a better way. Indeed, a better and more stable solution should play along with Python's import and packaging system and install your project as a local package using pip. Way to install a local package. When you install a package from PyPy, the package is available to all scripts in your environment. However, you can also install packages from your local computer, and they will also be mode available in the same way. Creating a local package doesn't involve much overhead. First, create minimal setup.config and setup.py files in the outer structure directory. So metadata name equals local structure version 0.1 options packages equals structure, which is the name of the file there. Setup import setup tools. In theory, the name and version can be whatever you like. However, they will be used by pip when referring to your package. So you should choose values that are recognizable and don't collide with other packages you use. One tip is to give all such local packages a common prefix like local or your username. Packages should list the directory or directories containing your source code. You can then install the package locally using pip. This command will install the package to your system. Structure will then be found on Python's import path, meaning you can use it anywhere without having to worry about the script directory, relative imports, or other complications. The /e option stands for editable, which is important because it allows you to change the source code of your package without reinstalling it. Note this kind of setup file works great when you're working with projects on your own. However, if you plan to share the code with others, then you should add some more information to your setup file. For more details on setup files, check out how to publish an open source Python package to PyPy. Now that the structure is installed on your system, you can use the following import statement. This will work no matter how you end up calling your application. In your code, you should consciously separate scripts and libraries. Here's a good rule of thumb. A script is meant to be run, a library is meant to be imported. I'm trying to think if I do this or not in my own stuff. It gets really complicated and confusing. If I have to do this every time, I'm gonna do a script or a library. Because sometimes you don't know if the stuff you're doing you're gonna run or just gonna build for other things to run. You might have code that you want should both run on its own and import from other scripts. In that case, it's usually worthwhile to refactor your code so that you split the common part into a library module. While it's a good idea to separate scripts and libraries, all Python files can be both executed and imported. In the later section, you'll learn more about how to create modules that handle both well. Namespace packages have been available since 3.3. Let's try to implement one. As a motivating example, you have another go at the problem solved in the factory method. Let's assume that you're lucky, blah blah blah. I think I'm gonna watch some videos. Introducing math import lib.resource. Import lib.resources gives access to resources within packages. In this context, a resource is any file located within an importable package. The file may or may not correspond to a physical file on the file system. This has a couple of advantages. By using the import system, you get a more consistent way of dealing with the files inside your packages. It also gives you easier access to resource files in other packages. The documentation sums it up nicely. If you can import a package, you can access resources within that package. How to publish an open source? So it's not this. Import lib.resources. Source code. Lib import lib resources.py. Do I have this? Oh, this is bugged here. I think I'm gonna try to open this again. Yeah, now it works. There's probably some problem that I don't know what happened there. So what is the thing here? Lib import lib resources by. Yeah, there's no. Oh, here. Import lib resources by. Nice. So it imports all this stuff. Package union string module type, resource union string OS path flag. Def get package module. Take a package name or module object and return the module. If a name the module is imported, if the past or imported module object is not a package, raise an exception. So I shouldn't use this function here, apparently. If as attribute package spec, if package spec module search location is none. Else module equals import module package. Def normalized path. Parent file name equals OS path split path. Let resources reader. Open binary, check location. This is where it starts to get confusing. Hopefully this will clear up with time. Clear up with time. The more exposure I get to this stuff. I remember on the beginning, everything is hard in the beginning, where I didn't know anything about coding and it seemed like very difficult and confusing to do. But then you just get used to it. And then it becomes like normal. You don't even think about it anymore. So hopefully the same thing will happen with this stuff. Just the initial phase is annoying because you don't understand anything. And you have to look it up things constantly. Just assume the loader is a resource loader. All the relevant import lib.machinery loaders are, and then attribute error for get data will make it clear what is needed from the loader. So loader cast resource loader package inspect loader. Read binary, read text, context manager. If the resource does not already exist on its own on the file system, a temporary file will be created. If the file was created, the file will be deleted upon exiting the context manager. No exception is raised if the file was deleted prior to the context manager exiting. Def path package resource. Try yield path reader. Resources are roughly akin to file inside directories, though it's important to keep in mind that this is just a metaphor. Resources and packages do not have to exist as physical files and directories on the file system. Note this module provides functionality similar to package resources, basic resources access, without the performance overhead of that package. This makes reading resources included in packages easier with more stable and consistent semantics. Following types are defined. Import lib.resources.package. The package type is defined as union string module type. This means that where the function describes accepting a package, you can pass in either a string or a module. Module objects must have a resolvable spec submodule search location. That is not none. Import lib resources resource. This type describes the resource names passed into the various functions in the package. In this package, this is defined as as returns and import ABC transversable object representing the resource container for the package, think directory and its resource think files. A transversable may contain other containers, think subdirectories. Package is either a name or a module object which conforms to the package requirement. As file, open binary, path. Return the path to the resources and actual file system path. This function returns a context manager for Use in a with statement. The context manager provides a pathlib.path object. Exiting the context manager cleans up any temporary file created when the resource needs to be extracted from, e.g., a zip file. Package is either a name or a module object which conforms to the package requirements. Resource is the name of the resource to open within package. May not contain path separators. Return true if there is resource named name in the package, otherwise false. Importers and path hooks. This module contains the various objects that help import find the load modules. Debug byte call. The thing is that none of this stuff. I'm not sure if it helps, but I'm not. I can't think of a way to use this stuff to do what I want to do. Class import lib.machinery.built-in importer, an importer for built-in modules. All known built-in modules are listed in C's built-in module names. This class implements the import lib, abc metapath finder, import lib, abc inspect loader, abcs. Only class methods are defined by this class to alleviate the need for installation. A finder for sys.path and package path attributes. This class implements the import lib abc metapath finder. Also, here's the find spec. Only class methods are defined by this class to alleviate the need for instantiation. Class method find spec. Full name, path equals none, target equals none. Class method that attempts to find a spec for the module specified by full name on sys.path. Mutable name tuple. Module spec. A namespace containing the import related information used to load the module. An instance of import lib machinery module spec. So module spec is what I'm trying to get. A specification for a module's import system related state. This is typically exposed as the module's spec attribute. In the descriptions below the names in parentheses give the corresponding attribute available directly on the module object. gmodule.spec.origin equals module.file. Note, however, that while the values are usually equivalent, they can differ since there is no synchronization between the two objects. Thus, it is possible to update the module's path at runtime, and this will not be automatically reflected in spec.submodule search locations. So it takes on a name, loader, origin was none. I kind of want to open this in the other thing and code along. That's the problem. I have to do two things at the same time, two monitors. So let me think here. Think what I'm gonna do is try to use these functions outside of the class. But then, yeah, not sure. Maybe you should just use sys, import sys, and then try to use these functions with the sys module. Sys.findSpec. Like, how do I call these functions? A string for the fully qualified name of the module, loader, the loader that should be used when loading the module. Finder should always set this. An object that tries to find the loader for a module that is being imported. There are two types of finder. Metapath finders choose with sys metapath, and path entry finders choose with sys path hooks. For division, mathematical division rounds down to the nearest. Yeah, this doesn't have anything to do with the finder. A list of metapath finder objects that have their find spec methods called to see if one of the objects can find the module to be imported. The find spec method is called with at least the absolute name of the module being imported. If the module to be imported is contained in a package, then the parent's package path attribute is passed in as a second argument. The method returns a module spec, or none if the module cannot be found. But how do I use that? That's the question. Your versions module path. How to use sys.meta path. Good old Stack Overflow. Given the one called blah blah blah. It's a pretty good description. Damn, there's so many tabs open. I get annoyed by these many tabs open. I have to close some of them. Which is unfortunate because I feel like all of them have stuff that I want to know. Finder for syspath and package path attributes. This class implements the import lib abc metapath finder. Class method that attempts to find a spec for the module specified by full name on syspath, or if defined known path. For each path entry that is searched, sys.path imported cache is checked. Sys.imported cache. If a known false object is found, then it is used as the path entry finder to look for the module being searched for. If no entry is found in syspath imported cache, then syspath hooks is searched for a finder for the path entry, and if found is stored in sys.path imported cache, along with being queried about the module. If no finder is ever found, then none is both stored in the cache and returned. Changed in version 3.5. If the current working directory represented by an empty string is no longer valid, then none is returned, but no value is cached. Sys.path imported cache. Class method find module. A legacy wrapper around find spec. Class method find module. So I guess you need to put this. So I'm gonna search what is a class method and how to choose find spec. Class method invalidate cache. Class method file finder. What is a class method? Class method is a method that's shared among all objects. For class method, put the class as the first argument. Class methods can be called from instances and from the class itself. All of these use the same method. The method can use the classes variables and methods. Class method example. To turn a method into a class method, add class method before the method definition. As parameter, the method always takes the class. The example below defines a class method. The class method can then be used by the class itself. This example, the class method uses the class property name. You can use a class method with both objects in the class. So apple and berry. But it's weird because when I create classes and I don't put this, it all works like this as well. The parameter name now belongs to the class. If you change the name by using an object, it ignores that. But if you do that by the class, it changes. Example below. Alternative writing, often the Pythonic notation is used. This is not strictly required. You can also use a class method like this. Class methods, fruit.print name. Class method versus static method. Like a static method, the class method doesn't need an object to be instantiated. A class method differs from a static method in that a static method doesn't know about the class itself. In a class method, the parameter is always the class itself. A static method knows nothing about the class or instance. You can just as well use a function call. Class method gets the class when the method is called. Knows about the class. I'm gonna watch a video about this. It's better. Path import a cache. A dictionary acting as a cache for finding finder objects. The keys are paths that have been passed through syspath hooks. The dividers are the finders that are found. If a path is a valid file system path, but no finder is found on syspath hooks, then none is stored. Change in version 3.3, none is stored. Instead of imp.new importer, when no founder is found. Platform. This string contains a platform identifier, so I guess this is a different thing. Blah blah blah. I have to look at one thing at a time, so I have to decide which thing I need to do it first. So first this class method, then find spec. Sure to create a meta path finder class which returns. So my idea now is try to use the find spec in a for loop. Then when it returns the name of each file, then I can do things with that name on a for loop. Ideally I want to put find spec for each name that is created in the for loop. So maybe I can make a list, then put all the names on that list, and then loop through that list and do the find spec again. And then I can make a function that does that and does that do that recursively. And that way I find all the imports. Then if I manage to do that, then I can think about the connections between them, which is gonna be harder, I guess. Which contains a loader. So I think that's the best plan. So I'm gonna close the other tabs and only focus on this. And then I focus on the other stuff. Otherwise I'm gonna get lost. Dependency injection with import hooks in Python 3. This meta path is one of the best kept secrets in the Python standard library. Despite being squarely located in a module every Python programmer is familiar with, some might say the secrecy is well warranted, though it's not usually a good idea to go messing around with tools and functions that may subvert programmer expectations the way this oddly named list potentially can. But isn't do not better than no not? So before a quick primer on dependency injection, let's examine some of the ins and outs of sys.metapath. Never use an import statement, say import OS, that's functionally equivalent to the following code. OS Dunder import OS. So this is already interesting. It's a mild oversimplification since stuff like submodules would require a little bit more work, as well as we'll have to deal with later, actually. But the main point should be made here is that the import built-in does the heavy lifting under the hood for module imports in Python. And now we know that it exists, we can examine its control flow. First, it checks sys.modules, a dict containing already loaded modules, just in case we've already imported the requested module before. Next, it checks sys.path, a list containing file system paths for Python to search through for potential modules. You probably know about this list already. However, if the sys.metapath list is not empty, then before looking through sys.path, every meta importer hook in sys.metapath will be queried before the file system is checked, giving us an easy way to intercept module imports and do all sorts of freakishly wonderful things, like dependency injection. So what is dependency injection? It's roughly an applied version of the dependency inversion principle. Dependency inversion principle. In object-oriented design, the dependency inversion principle is a specific form of loosely coupling software modules. When following this principle, the conventional dependency relationship established from high-level policy setting modules to low-level dependency modules are reversed, thus rendering high-level modules independent of the low-level module implementation details. The principle states, a high-level module should not import anything from low-level modules. Both should depend on abstractions. Abstractions should not depend on the details. Details concrete implementation should depend on abstractions. By dictating that both high-level and low-level objects must depend on the same abstraction, the design principle inverts the way some people may think about object-oriented programming. The idea behind points A and B of this principle is that when designing the interaction between a high-level module and a low-level one, the interaction should be thought of as an abstract interaction between them. This not only has implications on the design of the high-level module, but also on the low-level one. The low-level one should be designed with the interaction in mind, and it may be necessary to change its usage interface. In many cases, thinking about interaction in itself as an abstract concept allows the coupling of the components to be reduced without introducing additional coding patterns, allowing only a lighter and less implementation-dependent interaction schema. When the discovered abstracted interaction schema between two models, I think I got slightly the point of this, but not really. But I don't think it's important to understand now. So, because this is probably more important. It's roughly an applied version of the dependency inversion principle, often for module size stuff. Say your application has several different front ends, maybe targeting different platforms or UI toolkits. As long as you have a common interface, dependency injection would allow you to do something like this. Like this here. User info equals info underscore getter dot get user info. Front end equals dependency injector get front end. Display user info user. So what? I can do that already with a facade or something. Maybe a config switch. I can hear you say. For very simple use cases, that may actually be better. Simple is better than complex, remember? Yeah, I actually have no idea what he's talking about here, but I guess this is for more advanced people than I am. this article. However, with dependency injection, we can easily provide module level reuse, as well as significant tail on boilerplate. What if I told you by the end of this article you could write something like this? Import myapp.dependency.frontend. Is this Python? Yeah, it is. And let's just make sure. Yeah, import hooks in Python 3. Output style. One import that works regardless of whether we are using GTK plus Qt and curses or whatever your program needs to function. Might be thinking some very dark thoughts at this point. It's true, all sorts of dark magic could be performed depending on the details of our import hooks. Readability counts, so it's important that we not stray too far off the beaten path. So let's set some requirements for our dependency injection framework before writing our implementation. All dependency injection import paths begin with myapp.virtual. Provided dependencies are known beforehand and registered with a provide method. All the magic, and there's not all that much, relies almost entirely on creating a meta path finder and then adding it to sys.metapath. So it's the same thing the other guy did. Metapath finder is a very simple object with a single public method find spec. So class dependency injector finder import lib.apc.metapath finder def init. I can do maybe inside the function here. That's already done. Yeah, but how would I do that? Maybe I can create a list here. Goes empty string. Then name list.append name. And then for item in a list, I can do something. But how the bridge that I have to get to close the gap here is how do I take the name of the modules that are being imported and redo the process again to find the spec of those modules that are being imported, if they have any. Because I can't do this inside the find spec function on the class. But maybe I can just put the list here, and this is gonna return an object. But then I'll have to find when the object is gonna be returned. So that's the thing, I think. Can I call this outside of this class? Or maybe I can create a class in another program instead of importing. But let's keep reading and try to understand better. Relies almost entirely on creating a metapath finder and adding it to sys.metapath. A metapath finder is a very simple object with a single public method, find spec. So I have import lib.abc and .machinery. Class dependency injector finder, import lib.abc.metapath finder. Def init self loader. Write to loader in a minute, hang tight. Self.loader equals loader. Def find spec. I don't understand why there's a loader as well. Yeah, I'm gonna watch this video. I think I should probably watch a shit ton of videos about this until I really hammer in my brain the stuff to really understand. Because I think that's the most important part. We read this stuff and close the tabs. Path-based finder, one of the default metapath finders, which searches and import path modules for modules. But I feel like I'm already starting to get a little bit more than I did before I read all this. So that's good. Metapath finder, a finder returned by a search of sys.metapath. Metapath finders are related to but different from path entry finders. See import lib.abc.metapathfinder for the methods that metapathfinders implement. Of course, there's something else to read about. An abstract base class representing a metapathfinder. For compatibility, this is a subclass of finder. Change the version 3.10. sys.path, a list of strings that specifies the search path for modules, initialized from the environment variable. Python path, plus an installation dependent default. As initialized upon program setup, the first item of this list, path0, is the directory containing the script that was used to invoke the Python interpreter. If the script directory is not available, e.g., if the interpreter is invoked indirectly or if the script is read from standard input, path0 is the empty string which directs Python to search modules in the current directory first. Notice that the script directory is inserted before the entries inserted as a result of Python path. A program is free to modify this list for its own purposes. Only strings and bytes should be added to sys.path. All other types are ignored during import. So I'm going to close this as well. The import system. Import lib. One module gains access to the code in another module by the process of importing it. Import statement is the most common way of invoking the import machinery, but it's not the only way. Functions such as import lib.import module and built-in Dunder import can also be used to invoke the import machinery. The import statement combines two operations. It searches for the named module, then it binds the result of the search to a name in the local scope. The search operation of the import statement is defined as a call to the import function with the appropriate arguments. Then the return value of import is used to perform the name binding operations of the import system. I think what I'm gonna do is I'm gonna put this all in a list and then watch a bunch of videos about it. And read a bunch of articles. So I have the find spec, the cache thing. Now I forgot all the names. Should have done this before. That's not a problem though. I'm gonna keep this sys functions, sys classes and functions to study. Put it on caps lock so it's easier to see. The import system, packages, loaders, submodules, spec is also good. Spec attribute must be such the module spec that was used when importing the module. Setting spec appropriately applies equally to modules initialized during interpreter startup. The one exception is main, where spec is set to none in some cases. When package is not defined, spec.parent is used as fallback. These are the first things. Oh, cached is also good to know. And I think this is on the other list as well. So I'm gonna erase this one from this list. Module name. Sys path hooks. I think I'm gonna close this and keep reading the article. Let me do this. I think I stopped here. I was reading the function. Def finds back self full name path target none. Attempt to locate the requested module. Full name is the fully qualified name of the module. Path is such a path for submodule packages or none otherwise. Target can be a module object, but is unused in this example. If self.loader.provides full name, return self.gen spec full name. Gen spec self full name spec equals import lib.machinery.module spec full name self loader. We'll also add it to sys meta path later. If a meta path finder provides the requested module, then it should return an instance of import lib.machinery.module spec class, which is a fairly simple affair with a small handful of attributes that lets Python's import machinery know what it needs to know to take the next step in importing the module the user requested. For our purposes, we're interested in two attributes, the only required ones. Module spec.name, which is the name of the requested module, and module spec.loader, which is the loader object that Python should use to actually load the module. Also, the loader is the loader of the module. Yeah, makes sense. So first gets the name, then loads, then attaches to the namespace. Python should use to actually load the module. You'll notice the self.loader lines above that reference a loader object as well. A loader object is a very simple class with two required methods in modern Python. Create module, which takes a module spec as its sole argument and returns an object that Python will consider to be the new module, and execute module, which takes the new module as its sole argument and executes it. So a no OP bare bones loader looks something like this. So class loader takes import lib.abc.loader as an argument. Def create module self spec raise not implemented error, and then execute module self and module. In addition to those two methods, we should implement the provide method we talked about earlier to signal that a certain dependency is provided. In addition to the provides method that our finder referenced earlier, that indicates whether the requested module is part of our dependency injection framework. Here's the implementation. Class dependency injector loader. I'm gonna run the file that I built here just because I'm curious to see what happens. Item dot, maybe I would item dot find spec, but this is not gonna work. Probably. So here's what I've done. So create a list and append the name to the list and loop through the list and use the find spec. Oh, I don't have main here, so I have to import it again. It didn't print anything. That's interesting. Maybe if I do print here, but at least it didn't give me a bug. Doesn't show anything again. So I'm gonna do this and see what happens. It's not showing me anything. What the fuck? So is maybe something I changed here? because it's supposed to be working. So what's wrong here? Copy this, paste Ctrl Z a bunch of times. Maybe I changed something and don't remember. But this is the furthest that it goes. So why it's not showing? That's weird. I did reinitiate the pie chart. Maybe if I create a find object equals debug equals main debug finder, and then I click finder dot find spec scalar. Oh yeah, I was using a scalar. I don't remember actually if I was or I wasn't. Path. Yeah, I probably wasn't. I was just running the file, and it was showing me the print statements. If I run this file, maybe if I do this here, it will work. Yeah, that's probably why it wasn't working. Let's see now. No, still the same thing. Oh, it's because I'm importing main after I need to import it before. That's why. I guess. Yeah, and there we go. So it wasn't working because the module was loaded already. So well, now I lost everything that I did here. List equals this, then list dot append name for item in list print name print find spec find the right spec. Yeah, it's not gonna work. Can I write it out because of this? Maybe item dot find spec. Yeah, maybe now it works. String the object has no attribute find spec. What if I just do print item here? Let's see what happens. Now it shows the list. So maybe if I delete this, I just print list here. Yeah, so this is a list containing all the things. The issue is that they seem to be showing up each one in a different list instead of being part of the same list. So what that tells me that is this runs every time. Yeah, it runs for every module. That's why there's only one by list there. Otherwise, it would be a giant list with all of them. Yeah, but I still can think about a way to find a connection. So I guess I need more information. Self.dummy module provides self service name. Create module. Create a given module from the supplied module spec. Under the hood, this module returns a service or a dummy module, depending on whether Python is still importing one of the names in common prefix. Service name self-truncate name. Execute module. Execute the given module in its own namespace. This method is required to be present by import lib.abc.loader, but since we know our module object is already fully formed, this method merely not. Truncate name, strip off common prefix from the given module name convenience method when checking if a service is provided. There's simply a lot of code here at first glance, even though most of it is comments. So let's walk through these class methods. First are the provide and provides methods that we've talked about earlier. There's not a whole lot of magic present in either one. Create module returns a so-called dummy module if we're trying to import either myapp or myapp.virtual. There's a good reason for that. So say we have the following line of code. Under the hood, this generates three distinct searches in Python's import machinery. One for myapp, another for myapp.virtual, and lastly one for myapp.virtual.frontend. Since obviously myapp and myapp.virtual don't actually exist anywhere on the system, but Python will complain if they aren't loaded, we claim we provide both. Note how provides will return true if required for both myapp and myapp.virtual, and return an empty dummy module to placate Python's import machinery. Only when we encounter myapp.virtual.frontend do we check against the list of provided dependency injection services. At this point, we've actually written all the plumbing we need to. So let's wrap up and see how we'd use these classes in practice. So import sys class dependency injector. Convenience wrapper for dependency injector loader. So self.loader sys def install sys.math metapath append self.finder provide self.loader provide if name equals main injector equals creates the object here of the class injector.provide front end module injector.install installs the appends the class to the path system meta path. At this point, it'd be worth it to take a step back and examine at a high level what's going on behind the scenes. The call to injector install appends our dependency injector finder onto the sys metapath list, so Python will use it for future imports. The line import myapp future virtual frontend triggers three module searches as mentioned earlier. One for myapp, then myapp virtual, then myapp virtual frontend. Python comes through system.metapath looking for metapath finders. If your system Python is anything like mine, our dependency injector finder will be the only one not defined by frozen import lib, which is a part of Python itself. For each found metapath finder, Python queries the find spec method, seeing if the finder provides the given module. Obviously, my app.virtual.frontend doesn't exist on the file system, so it falls to our metapath finder to handle it. In all three cases, we return a module spec instance with name set to the same name that Python asked if we could find. A loader set to our custom dependency injector loader. Next, Python will call the create module method on our loader for the module spec in question. For my app and my app virtual, our loader recognizes that these are dummy modules and returns the same dummy module for both, tricking Python into believing the module was loaded. It returns the instance of front-end module we gave it with injector.provide upon being asked to load my app.virtual.frontend. Python allows any valid object to function as a module, so applying all the class is perfectly fine to return. Python will finally call the exec module method on our loader, passing it the object we returned from create module. I don't think I'm going to read the rest of it. As I mentioned earlier in the article, it's important not to abuse language features like this. With great power comes great responsibility. After all, and this especially rings true when it comes to meta programming. Still, there's a time and place for everything, import hooks included, but please use them responsibly. Finally, the complete code example is yeah, I'm not sure if I understand. To printers, I didn't know about sys.metapath. Seems also very hard to develop it. Very handy to develop plugin systems like it. Great for a big customizable app. More suggestions if you re-edit your post, you can add syntax highlighting with tags like this.
Hey everybody, how's it going?
So I think I'm gonna watch a couple of videos now on these topics. The main thing that I wanna know is how to do this outside here. Let me do something before I watch the videos. I wonder if I can call this class there. Find equals main.debug finder. Yeah, it's gonna ask me for the path. That's the problem. What is the path on find spec arguments? Sys meta path. Maybe I don't need to put find spec. To require position arguments, name and path. But I don't understand why this works when I run it just on the file alone. Maybe 0 and let's try this. None. Yeah, it's wrong. Maybe I need a better understanding of C++ as well to be able to do this properly. But I don't think so. I'm not sure, but I think it's possible. I think I'm close to being able to do what I want to do. This module stores imported modules. I just need to be able to know how to do things with these names that I'm getting. Let me try to run this file. Runs, but I need to get these names and do the things with them. I'm gonna open up the thing there. Now it's too bright. See how many hours I've been here. 2.5 hours already. Find spam. I think I still don't have enough, even though it seems like I'm very close, but I still don't have enough information to be able to do it. What if I put like this and run? Now it doesn't show anything. What if I import C's here? Also doesn't show anything. Because it's built in, probably. Find the load function takes an absolute module name and performs the following step. The module is in sys.modules return it. Initialize the module's search path to none. The module has a parent module. The name contains at least one dot. Import the parent module if it's not in sys.modules yet. Set the module search path to parent's path. Find the module's spec using the module name and the module search path. The spec not found, raise module not found. Load the module from the spec, add the module to the dictionary of the parent modules. Return the module. All imported modules are stored in the sys.modules dictionary. This dictionary maps module names to module objects and acts as a cache. Before searching for a module, find and load checks sys modules and returns the module immediately if it's there. Importer modules are added to sys modules at the end of step 5. If the module is not in sys.modules, let me see if I can search to find. But I was gonna search for how to find module dependencies, but dependency tree of a Python module. Generally, many Python packages are dependent on other packages, but how do we know that on which package is a module dependent? Pip phrase. This is a built-in Python. This is a Python built-in module that can help us know dependent packages, but it shows all dependencies as a flat list. Find out which are the top level packages and which packages do they depend on requires some after. Let us see an example of how it works. Nice, so this is what I'm looking for. Hopefully it's gonna allow me to see this. Pip freeze. Outputs equals this. Pip depth tree utility. One easy way of doing so is to use the pip depth tree utility. The pip depth tree works on the command line and shows the installed Python packages in the form of dependency trees. This module does not come built in with Python. To install it, type the below command in the terminal. Install pip depth tree. Install pip depth tree. Install pip depth tree. It works. Very satisfying. Nice. This will install the latest version of pip depth tree, at least Python 2. Now run this command on command prompt to get a dependency tree of all your Python modules. Pip depth tree. Pip depth tree. Nice. So now I have to investigate how this works. And then I want to transform this into a tree visualization instead of the terminal. And this is a shit ton of packages here. Hopefully they have on that. Let's see what happens when you use pip depth tree and freeze all together. Combining pip depth tree and freeze. Output equals this. So here we see that using pip depth tree along with freeze shows the output by combining the properties of both commands. So it looks like the output of pip freeze indicates which that package installed which another package. Similar to pip depth tree, but here indentation is used instead of a hyphen to indicate tree. Warnings in pip depth tree. Commonly there occur two types of warnings while executing pip depth tree command. Let's see them one by one. Conflicting dependencies. As the name suggests, conflicting dependencies is so is relevant. Huh? Sometimes there are packages that are specified as dependency of multiple packages of different version. This situation possible conflicting dependency warning arises. So any package that's specified as a package of multiple pip tab tree. Pip doesn't have a true dependency resolution yet. The warning is printed to standard error instead of standard out. To completely silence this warning, use the /w silence or /warn silence flag. It can also be made both strict with warn fail. Note the warn flags added to clear dependencies. Commands using pip directory external tools. Uses flag JSON to show output in JSON representation, as shown below. Pip tab tree JSON. Nice. So it has the name of the package. Can you use this on the file though? Because ideally I would take this as an object and then do stuff with the object. So I forgot to write this on the file. Pip tab tree JSON. Note dash JSON will output a flat list of all packages with their immediate dependencies. To obtain nested JSON, use JSON tree added inversion. Output a flat list of all packages with their immediate dependencies. So that's the JSON. I think it's both. Yeah, JSON tree. Nested dependence. Nested JSON. Flat list. Standard setup by as this document where I can find is way to access from either Python or the command line. Really, I'm looking for something like this. How to run pip tab tree. The pip show package name command. There's pip tab tree. From pip vendor import package resources. Dash resources. But a few answers here show pip being imported for use in programs. Documentation for pip is strongly advised against this usage of pip. Sort of accessing package being imported. Import pip. That one I use on the terminal. Yeah, then I'm gonna use print. Let me. Oh, it's gonna run anyway. So let me take this out temporarily. Yeah, but it doesn't show the thing. How do I actually run it? Yeah. It's not gonna work. Dependency graph can also be visualized using graph vis. Nice. So someone did this already. Huh? But the graph vis is an optional dependency, i.e. required only if you want to use graph output. Graph vis. Graph vis layout programs takes description of graphs in a simple text language, make diagrams in useful formats such as images and SVG for web pages. The current release, download here. Use pip install graph vis. Pip dip dep3 graph output PDF PNG. I wonder if I can get it from one specific. One specific program. First packages. So let me type these commands before I forget. I'm gonna copy this, put it here as well. Pip dep3 graph output PNG. And when necessary for the output option, please install it. Nice. I'm gonna close the window a little bit. Okay, now it's done. Let's try again. Pip dep3 graph output PNG and dependencies.png. There's no attribute formats. Maybe I should just try to do it with pip dep3 graph output and dependencies.png. See what happens. Expected one argument. So this doesn't work. The graph is an optional dependency required only if you want to use graph output. This version 2 points package in reverse, flags are as part of for all output formats, text, JSON, JSON tree, and graph. Earlier versions JSON, graph output options override package in reverse. Usage pip.p3 by dependency tree of the installed Python packages. Please Python. Show this help message and next it show program's version number. Install depths at top level. Graph output formats. I'm gonna search for this. Graph is backend, has no attribute formats. It would seem that there was a very recent change to graph is that should obfuscate its internal. Am I also reply? Short term, you could downgrade your GraphViz module. It looks like 0.18 was the last tag before that submodules were made of back. Moving forward, you may wish to create an issue and our pull request against sklearn pandas repository to replace graphviz.backend.formats with graphviz.formats. I don't think I wanna do this stuff right now. I wanna keep going, but I'm getting tired already. So I think I'm gonna watch videos. No. Maybe this works. Con install Python graph. Oops. Hopefully this works. So there's two approaches now. One is to use this pip.tree, which seems to be the easiest one if it works. The other one is to figure out how to use the sys.metapath to create a list of the things and then create a graph from there. So I'm gonna watch videos while that loads there. The problem is that nobody makes videos about this stuff. So there's no other option but reading the stuff. I think I can close this page now. I'm probably gonna close this one as well because I already read this. And now let me watch these videos.
In our last video, we looked at the difference between instance variables and class variables. And in this video, we'll be learning about the difference between regular methods, class methods, and static methods. And a lot of people get confused as to the difference between class methods and static methods, so we'll definitely go over that in detail. So as we learned in our previous videos, regular methods in a class automatically take the instance as the first argument. And by convention, we were calling this self. So if a regular method automatically takes in the instance as the first argument, then how can we change this so that it instead automatically takes the class as the first argument? Now to do that, we're going to use class methods. And to turn a regular method into a class method, it's as easy as adding a decorator to the top called class method. So let's go ahead and create one of these. So I'm going to create a new method here with that class method decorator, and I'm just going to call this set raise amount. Now for this set raise amount method, I'm going to take in the class, and I'm going to take in an amount. And for now, we'll just put in a pass statement there. Now, if you'd like to learn more about how decorators work, then you can watch my video that goes into that in depth. But basically, this is altering the functionality of our method to where now we receive the class as our first argument instead of the instance. Now, by convention, with a regular method, it's as easy as adding a decorator to the top called class method. So let's go ahead and create one of these. So I'm going to create a new method here with that class method decorator, and I'm just going to call this set raise amount. Now for this set raise amount method, I'm going to take in the class, and I'm going to take in an amount. And for now, we'll just put in a pass statement there. Now, if you'd like to learn more about how decorators work, then you can watch my video that goes into that in depth. But basically, this is altering the functionality of our method to where now we receive the class as our first argument instead of the instance. Now, by convention, with a regular method, we called this instance variable self. And there's a common convention for class variables too, and that is CLS. Now we can't use the word class as the variable name here because the word has a different meaning within the language. You can see here up at the top that we use the word class to create a new class. So that is a keyword in Python. So instead we're going to use CLS as our class variable name. So now within this set raise amount method, we are working with the class instead of the instance. And to show you what I mean by this, let's go ahead and set our class variable raise amount. So we'll say class dot raise amount. And we'll just set this equal to the amount argument that we are accepting from this method. So now down here at the bottom, I still have these two employee instances that I created in our previous tutorials. And here I'm printing out the classes raise amount as well as both instances raise amount. So if I go ahead and run this, then you can see that all of those are equal to 4%. Now the reason all those are equal to 4%, again, is because we have this class variable here, raise amount, that is set to 4%. So now let's say that we wanted to change this to 5%. So before I print these out, then I could just use that set raise amount method that we just created, and I could do employee dot set raise amount, and it automatically accepts the class, so we don't have to pass that in. So now we can just pass in an amount. So I'm going to go ahead and do 5%, and if I save that and run it, then you can see that now all of these are equal to 5%. Now the reason all those are equal to 5% is because we ran this set raise amount method, which is a class method, which means that now we are working with the class instead of the instance, and we're setting that class variable raise amount equal to the amount that we passed in here, which is 5%. So really, us running this set raise amount method here and setting this CLS variable raise amount to the amount is the same thing as us saying employee dot raise amount equals 5%. But now we are using this class method to do that instead. Now you can run class methods from instances as well, but that doesn't really make a lot of sense, and I don't ever see people doing it. But to show you what that would look like, I can also grab this instance here, and I can run that class method from the instance. And if I run that, you can see that running that class method from the instance still changes that class variable and sets all of the class variable and both instance amounts to that 5% that we passed in. Now you may also hear people say that they use class methods as alternative constructors. Now what do they mean by this? So what they mean is that you can use these class methods in order to provide multiple ways of creating our objects. So let's say that, for example, we had someone who was using our employee class, and they said, hey, I have these specific use cases where I'm getting employee information in the form of a string that is separated by hyphens, and I'm constantly needing to parse the string before I create new employees. So is there a way to just pass in a string and create an employee from that? So let's go ahead. I have an example down here to where we can see exactly what this problem would look like. So let's say that this is a common use case for how someone is using our class. We have 3 strings here that are employees separated by hyphens. So we have the first name, the last name, and the salary, and they're all in a string and they're separated by hyphens. Now, if I wanted to create a new employee from this string, then what I would have to first do is I would have to split this string on the hyphen, and then we would have our first name, last name, and our pay. And then based on those values, we would be able to create a new employee by passing in those values, and that would run our init method. So now let me go ahead and save this and run it. And you can see that this works. We're splitting the string up into a first name, last name, and pay. And then we are creating a new employee, just like we did up here, out of those values that we parsed from the string. And you can see that it works because we're printing out that new employee's email and pay, and everything is as it should be. But if this is a common use case for how someone is using our class, then we don't want them to have to parse these strings every time that they want to create a new employee. So let's just create an alternative constructor that allows them to pass in the string, and we can create the employee for them. So I'm going to go ahead and come up here and create a new class method. And we're going to use this new method as an alternative constructor. And usually these start with the from, but that's just a convention also. But I'm going to call this from string. And remember that we automatically accept the class as the first argument there. And I'm just going to call this second argument employee string. And now we're just going to go ahead and parse this string for them. So exactly what we did down here. I'm just going to grab this line, first name, last name, and pay. And I'm going to go ahead and put this in our class method. But now, instead of working with this specific string, I'm going to split the string that they pass to this method. So instead of employee string 1, I'm going to use this employee string argument from this method here. And down here at the bottom, we created our new employee by saying employee and then passing in those variables that we got when we split. But now that we're inside of our class method, we can do the exact same thing, but now we're going to use our class variable instead of employee because those are the same thing. So I'm going to go ahead and grab this line here and paste it in, but now I'm going to use this class instead of employee since that's basically the same thing. So this line is going to create that new employee, and now that we've created that new employee, we also need to return it so that they can receive that employee object when this method is called. So I'm just going to return that new employee object. Okay, so now our alternative constructor is done. So now I can delete this line here, and now instead of someone needing to parse the string themselves, we've provided them with this from string method that they can call. And you see here that they are just passing in this employee string 1. And it comes in here and it splits that string on the hyphen and then creates a new employee object and then returns that employee object. So now if I save this and run it, you can see that we got the exact same values. So now they'd have no need to parse these strings anymore. We've provided them with a from string alternative constructor, and now they can just pass in those strings and get their new employee objects. So when people say that they use class methods as alternative constructors, then this is what they mean. Now, if you want to see a real-world example of this, then I have the datetime module pulled up here, and there are several ways that we can create new datetimes. And if you search for class method within the datetime module, then you can see an example of some of these. So the default way of creating a datetime object is to say something like datetime and then pass in the year, month, and date. But if we look here at these class methods, which are alternative constructors, then what they do is they have this from timestamp, and you can use the current time, which is today. And they have a couple of other examples here as well. And you can see that they're basically doing the same thing that we just did in our example. So you can see that they are accepting the class and a timestamp with this from timestamp constructor. And then they are parsing out some dates, and then they're creating that new datetime object and returning that. So it's a new way of creating datetime objects. So that is very similar to the example that we just wrote on our own. So now if you ever see something like this in code, then you'll know what's going on. Okay, so now that we've looked at class methods, now let's talk about static methods. Now, a lot of people get class methods and static methods confused. Now, when working with classes, regular methods automatically pass the instance as the first argument, and we call that self. And class methods automatically pass the class as the first argument, and we call that CLS. And static methods don't pass anything automatically. They don't pass the instance or the class. So really, they behave just like regular functions, except we include them in our classes because they have some logical connection with the class. So let's go ahead and take a look at an example so that we know what we mean here. So I'm going to go ahead and delete these lines here. So let's say that we wanted a simple function that would take in a date and return whether or not that was a workday. So that has a logical connection to our employee class, but it doesn't actually depend on any specific instance or class variable. So instead, I'm going to make this a static method. So to create a static method, it's just as easy as a class method, and we're also going to use a decorator. That decorator is going to be static method. So I'm going to call this method isWorkday. Now remember, static methods don't take the instance or the class as the first argument, so we can just pass in the arguments that we want to work with. And I'm going to take in a day here and return whether or not that is a workday. So to make this a simple example, I'm not going to do anything too complicated. I'm just going to return whether or not our day falls on a weekday. So in Python, dates have these weekday methods where Monday is equal to 0 and Sunday is equal to 6 and all the other days in between. So if I wanted to return whether this is a weekday, then I could just say day.weekday. If that is equal to 5, which is a Saturday, and I'm going to go ahead and just copy this line here and say, or if that day is equal to 6, which is a Sunday, then I'm going to return false. And if it doesn't hit that conditional, then it means that it's a weekday. So I'm just going to return true. Now, sometimes people write regular methods or class methods that actually should be static methods. And usually a giveaway that a method should be a static method is if you don't access the instance or the class anywhere within the function. So say that I had this class method up here. You can see that I'm using that class variable there. But if I wasn't using it anywhere within that method, then it probably doesn't need to be a class method. And the same with regular methods. If you're not using that self variable, then you probably want to check and see if that would be appropriate to use a static method in that place. Okay, so now let's go down here and see if our static method is working. So I'm just going to go ahead and uncomment out these couple of lines here. And all I'm doing here is I'm importing the datetime module, and then I'm creating a new date. And if I wanted to use our new static method here that checks whether this date is a weekday, then I can just print out the employee.isWorkday and pass in that date. So if I run that, oh, and I got an error there because whenever I copied and pasted, I forgot to take out this second if. I really want that to say if the weekday is equal to 5 or the weekday is equal to 6. So now if I save that and run it, then you can see that this day that I passed in is false because that's actually a Sunday. Now if I replace this with the 11th and run that, now you can see that it's a Monday, so you can see that isWorkday returns true. Okay, so I think that is going to do it for this video. In this video, we learned the difference between regular instance methods, class methods, which can also be used as alternative constructors, and static methods, which don't operate on the instance or the class. So I hope all of that made sense to everyone. But if you do have any questions about anything that we covered, then feel free to ask in the comment section below, and I'll do my best
Understand
that
the
we just
static
did in our
methods.
example. So you can see that they are accepting the class and a timestamp with this from timestamp constructor, and then they are parsing out some dates, and then they're creating that new datetime object and returning that. So it's a new way of creating datetime objects. So that is very similar to the example that we just wrote on our own. So now if you ever see something like this in code, then you'll know what's going on. Okay, so now that we've looked at class methods, now let's talk about static methods. Now a lot of people get class methods and static methods confused. Now when working with classes, regular methods automatically pass the instance as the first argument, and we call that self. And class methods automatically pass the class as the first argument, and we call that CLS. And static methods don't pass anything automatically. They don't pass the instance or the class. So really, they behave just like regular functions, except we include them in our classes because they have some logical connection with the class. So let's go ahead and take a look at an example so that we know what we mean here. So I'm going to go ahead and delete these lines here. So let's say that we wanted a simple function that would take in a date and return whether or not that was a workday. So that has a logical connection to our employee class, but it doesn't actually depend on any specific instance or class variable. So instead, I'm going to make this a static method. So to create a static method, it's just as easy as a class method. And we're also going to use a decorator. That decorator is going to be static method. So I'm going to call this method isWorkday. Now remember, static methods don't take the instance or the class as the first argument, so we can just pass in the arguments that we want to work with. And I'm going to return all the other days in between true.
So now I get it.
Say if.
Nice. And this is the article I should read. Yeah, I think I'm gonna stop here today. We're gonna continue this tomorrow. Python plugin system. Wonder if I can press. Proceed.
Hello and welcome back to Algo Today I'm going to tell you how to install Graphics and how to fix the error Graphics executables not found. You guys might have already installed Graphics, but after installation you might get the error as Graphics executable not found. Okay, so let's fix the issues. So I have already put some of the steps here. You just need to follow the steps and you will fix the issue. So first you have to install Graphics in your Anaconda prompt. For that you need to type conda install python graphics. You might have already tried pip install graphics or conda install graphics, but remember you need to type conda install python graphics. Once you've done that, then your graphics has been installed in your Anaconda folder. So what you need to do, you need to go to the directory, you have to copy the path, and then you need to add that part to the control panel or to the system. So this is where you need to do step by step. So let's do it. So first you have to go
Oh,
to
I have
your
to edit
Anaconda prompt, and then you have to type conda install python
That's the
graphies.
problem.
Once you've done that, your graphies will be installed in your Anaconda folder. Then you go to your Anaconda folder. This is your Anaconda folder, and here inside Anaconda folder you will get one folder called libraries. So inside libraries you go to bin, and inside bin then you have to go to graphics. Here the graphics has been installed. So open that. Now you can see this is the path. Okay, so this is the path. You have to copy this path and you have to add this path to your system. So how to do that?
Let me do that. I think I'm gonna change the screen. Oh great, there is no file. I hate to see this happen.
You copy the whole path, okay, and then you have to go to your control panel. This is your control panel. So sorry, this is your control panel. So now you have to click on system and securities. Inside system and securities, then you have to click on system. So I have already put all this in this file, so you no need to worry. So you can just follow this file step by step, you'll get it. So inside this you go to advanced system setting, and then you have to click on environment variables, and then you have to go to path, and then you have to go to edit, and then here you click on new. The moment you click on new, there will be new box here. So if you notice, here is already this path I have already added here. Okay, so the same path which I copied I have already added here, so I am not adding, but you have to add it here. So click on new, and then you paste it here, and then okay. So the moment you do that, this path has already been added to your system. So now you go and try in any IDE or Jupyter Notebook import graphics, you will not get any error. Hopefully this video help you to fix the error. And this is a decision tree graphical representation, which I have already made a separate video for that. What is the Python code and how you can do a graphical representation of a decision tree? For that I have already made a video, and that link I will put in the description, and you can go through that. So hopefully this video will fix your issue, and have a great day. Please don't forget to like, subscribe, and put any comment if you want to
Yeah,
have
I
a
don't know
video for me.
where
I'll do that.
this
Thank you so much
shit
for watching this
is.
video, and have a
Maybe I
great
can
day.
use get source. Hey, what's up, man? Or girl. Or whatever in between. And you can use this spec. Yeah, so hey man, what's up? Oops. Yeah, but it's gonna give me a mistake. Cool. It's not defined. What happened here? What? What the hell? I was looking to find a way to create a graphical representation of library dependencies in Python. Yeah, I don't know how I did that. It was out of nowhere. No, I don't know how to put it back in. At least there is a new one here. Maybe if I put it here. How does this happen? Crazy. Yeah, so far I found this pip depth tree thing that apparently gets. He uses a thing named graph this that gets that makes the graphical representation for you, but I'm not being able to use it because it requires this encoding thing. So I have to put it on the path variable of the computer. Similar to ones to visualize the class hierarchy of a lib. Really? Yeah, I wanna create a not necessarily create if this exists. Obviously, I'm gonna use the one that exists, but I wanna have a visual representation of all the libraries and how they are connected, so I can study the source code of the sklearn library. How do you have any tips on best approach? And this is too long. It's the file for pip dep tree, I guess. Also here, there's another method that I should probably look at eventually. I think I'm gonna put it here. There's so much stuff. So much stuff. Yeah, this is the stuff that I'm looking at. Yeah, you gave it a class or a list of classes and then create a graphics of class, just subclass. No, here I just use it. On this one, I use the inspect here, this terminal, to get the source of the pip dep tree, which is supposedly the thing that allows you to see the package dependencies. From graph is import backend diff graph. So maybe I can use this one. Where is it? Here. Maybe I can do it like this. Also, a class.mro gives you all parent classes of that class. Really? That's good to know. I'm gonna write it here on the other stuff. Maybe I should write the Dunder, the other Dunder. This thing here. Add property, not Dunder. Just study later. It gives you. So you have to use, like, let's say I have a class named dog. Dog I use like this, right? The name of the class and then the method inside a print statement. Class name, it returns a tuple. Yeah, good to know, but for the thing that I'm doing specifically, this is not gonna. I think maybe later on, if I decide to amplify the things more. But I'm trying to find the connection of imports of the libraries. Because so far, every library that I saw, that I was studying, it has a lot of dependencies of other libraries. And I want to understand the connection between all of them and which ones show up more often. So I can study the source code of the ones that show up more frequently. And so I can also have a visual representation of how the programs are, the flow of information of the programs. Method resolution order, and to be specific, it is the order in which Python looks for methods. If it can't find it, find it in the first element of the tuple, looks for it in the second element, and so forth. Nice. Do you know about the sys stuff? Sys. I was trying two approaches, and then I've learned about this stuff here, which is a find spec method, which apparently returns the name of the module dependencies. Not the module dependencies, returns the name of the all the libraries that another library has. Let me show you what it does. So if you put this print statement here, yeah, I'll show you here. Was on this file that I was doing this? Yeah, so main is the thing that I have this sys thing, right? So I'm gonna put main here, import main. Then it's gonna run main as the file loads, right? And it's gonna execute this. And this, I don't understand really well what this is, but it apparently is a way for the Python importer thing to import functions, to import libraries. It's part of the system library that allows other libraries to be imported. And this inserts this debug finder, which is this class that some tutorial told me to do, which has this find spec inside this class method. And apparently this class method is used when you want a function to change the class in which it is inside. So the find spec changes the class of debug finder. And that's this CLS here, stands for class. So when I run this file, it's gonna print the names of the sklearn library, or the pipdep tree here. Yes, yeah. So each library that imports, it prints according to this. Importing, then name here. And these are all the libraries that pipdep tree uses. But the only issue with this approach is that it doesn't show the other connections between them. And it doesn't show the libraries that these libraries depend on, I think. So one approach is to do it like this, to try to figure out a way to use this stuff here from this name to find the connections and amplify the tree, and then build a graphical representation of that somehow. And another way is to find, which is probably easier, is to find out how pipdep tree works, and then try to use the graph viz of pipdep tree to get the graph. But apparently you need to put in the environment variables of the system. And then, yeah. Yeah, but I don't think I'm gonna be able to do this today. Find spec, Python. Let me run this again and see. Maybe, oh, so I accidentally pressed something there that made this thing pop. So after I'm able to do this, I'm gonna probably be able to study the sklearn library a lot more efficiently. At least I hope so. Because there's too many files here to understand. Yeah, this requires Bernoulli RBM, LMP classifier. It would be nice to know where this come from so I can find it easier. I have to spend a bunch of time looking at each one. And also visualizing things makes it much easier to understand the workflow of the programs. Stochastic optimizer. So I'm looking deeper. So modules dependencies are defined in its setup.py file, which is a Python script, so it's not really easier to grab it from that. So modules dependencies. So let's say here, setup.py. Oh. Yeah, but here it says from sklearn.build it with use imports synchronize this. Search for install requires on the Google, you mean, or DuckDuckGo? Setup.py. Oh, Control F, right? Apparently, there's no results here. Yeah, there's no results for. And the thing is, I would need to be able to do it programmatically as well, right? Not manually. But here there's config.add subpackage. So here there's a list of the packages. Maybe they do it strangely, which is why it is not really easier with this approach. Yeah, I think is this thing right here, right? Add subpackages. But the thing is, if I do it like this, if I take this approach, then I have each library is maybe it's gonna be different, maybe it's gonna be the same. I think the better approach is to try to understand the imports, the way that Python imports things, because then it's gonna be the same connection every time to find the flow of the things. Simpler lib. Do you have suggestions? SciPy, I don't know which one. Maybe NumPy. NumPy is simple, or regex. There's also a difference between built-in libraries and add-on libraries. Built-in libraries are from the system itself, and apparently the path is different. When the Python import thing is loading the files, it's a little bit confusing to understand, but yeah, same thing here. Config.add subpackages. So I guess it's the config file that sets up the packages. This is platform equals 32 and us path is directory. Back. But I suspect it's gonna be different for each one. Similar but different. Or maybe not, maybe they are all the same. these globals here, second time I see this, I don't understand what this is. Maybe it's getting global variables or something like that. For naming info, globals items. There's a lot of stuff that is kind of just on the code, but it doesn't have any obvious connection. That's the hardest part of studying through the source code. You're doing something very strange. Yeah. Apparently. Do you know what the globals mean or any of these things? NumPy is still. Yeah, so it's like I imagine, all global variables. But where is it defined? Where's the connection? So it gets all the global variables of the project and attaches to the variable G. Yeah, but apparently some of these things do that. I think on the sklearn also does that. Let's look at the Seaborn library. Yeah, they don't have a config here. So maybe another one. They have config here. Global config, but they don't have global. Yeah, I remember looking at this. They don't have global variables. No. Some modules which do not have their own setup.py must manually add submodules, submodules and tasks. Submodules with build utilities. Oh, this is the setup file. What? Bit more experimenting. Yeah, don't worry, man. For me, at least, it's really hard. But I'm kind of new to programming as well, so I spent probably around 3 hours now trying to figure this out. Probably will spend a lot more trying to understand everything. And the more you learn and you research, the more stuff shows up to research. The function I used as a pretty nice warning. This function should be used for internal and specialized purposes only. It's not guaranteed to exist in all implementations of Python. Yeah. Like, look at this. There's like 11 libraries here. 2, 3, 4, 6, 15 libraries. Utils seems to be shows up a lot as well. So I imagine it's something like the Sys library. I remember writing somewhere to search that, but let's write here again. Oh yeah, what is on the list of libraries to study? Required parameters, step, deprecate positional args, step, memory verbose. What is verbose? No. More words than necessary. Transformers equals estimators. Estimators. 13 transformers. Again, this has attribute. Should probably look this up as well. Yeah, so far I'm learning a lot of things. And it's weird that not a lot of people talk about these things, and they seem really important. Because every big library has these things. Maybe it's because it doesn't get a lot of views if you talk about it, because it's more specific. But I think it will make sense that at least some people talk about it. I guess the Corey guy talks about it, about some of this stuff. The law less estimator should be none as an identity transformation. Def feeder, final. Leave, get item. Pipelines that's only part step 1. Add property also shows up a lot. I added here. Yeah, so I think I'm gonna do this another time. I'm kind of tired already. Spent a bunch of time trying to search this. So tomorrow I'll probably look these things up and watch a bunch of videos and try to study all of these new things that I have here. Probably starting with pip-dep3 and graph-vis. Trying to put that on the environment thing. So yeah, see you.